Hello and welcome to our channel wherein we are covering the non-ideal IV effects of a MOSFET, and today we'll be wrapping it up as well. So today's topic will be starting off with something called as tunneling. Okay, so first topic for today is tunneling. So now we are well accustomed with this word, right? Where did we hear this thing before? Not the tunnels through which trains travel. This I'm trying to point it towards the quantum physics. Okay, I'm trying to point this towards the quantum physics tunneling. Okay, what was it? That we have an electron, and let's suppose there are some barriers in its path, and that electron has to reach from point A to point B. So instead of the electron traveling and facing all the obstacles in this way, what is supposed to happen? That the electron will tunnel through this. Okay, electron will tunnel through this. So I'm talking about that tunneling, but of course I'm talking about tunneling in MOSFET due to non-ideal IV effects. So we will check on that part. Okay, now in one of my classes I was telling you that we have the iPhone 14 Pro model wherein they, the purple color one, okay, I'm talking about that one. So in that they had advertised in the Apple event that they are using a technology of 4 nanometer. Whenever you hear any kind of electronics device wherein they're talking about a technology file, okay, so if you ever come across this word technology file, and beside it they will give you a number followed by a measurement. So understand that the whole design, okay, the whole design of that device okay means what? That each and every transistor has channel length of 4 nanometer. Okay, so in iPhone 14 Pro they had advertised that they're using a technology file of 4 nanometer. So from there we have understood that in that phone, if you have iPhone 14 Pro or 14 Pro Max, you need to understand that all the transistors, whether it's a MOSFET or a FinFET, they are using channel length as 4 nanometer. Okay, now there was this another flagship phone, that is Poco F1. Okay, and in that it was having a flagship processor, and in that they had used the technology file of 10 nanometer. That means in this phone's processor, all the transistors channel length was 10 nanometer. Okay, it was 10 nanometer. Now although there was a, now Poco F1 came up early, then came our iPhone 14 Pro, right? So now it got reduced. Poco F1 was launched, I think, I'm not so sure about it, I think it is 2018 or 19, somewhere there, and for 14 Pro I guess it was that 2022 to 2023, somewhere in that range, right? You can check on it. I might be, not remembering it correctly. So even if, let's suppose it was 2019 and iPhone in 2022, so in a span of nearly 3 years, the channel length got reduced from 10 nanometer to 4 nanometer. Okay, that means if the channel length is reducing, if the channel length got reduced from 10 nanometer to 4 nanometer, that means the overall transistor dimension also got reduced. It got scaled down, isn't it? So if we keep on reducing, the technology file further more, let's suppose it becomes 2 nanometer. Okay, in the near future, if it becomes 2 nanometer, the research is continuously going on in this. Okay, what will happen? There will be certain repercussions also. See, beyond a point, you can't scale any dimension down. Beyond for every phenomenon, there is a limit. Okay, so if that happens, now if I keep on reducing from 4 nanometer to 2 nanometer, there will be some side effects as well. Okay, now as the technology file gets scaled down, okay, as and when the technology file gets scaled down, what will happen? The thickness of oxide, TOX, remember in our ID current equation derivation, this thickness of oxide will also go down, because if this is a parameter of the device design, isn't it? So if I am scaling down the transistor itself, don't you think the thickness of oxide will also get scaled down because of that, isn't it? So this thickness of oxide, it is solely dependent on the technology file. So for 10 nanometer, I will have a different TOX, and for 4 nanometer, I'll have a different TOX, and for 2 nanometer, I'll have a different TOX. So it is completely dependent on the design. Okay. So now why am I pointing this? Why is this important? It's okay, na? It was anyways a constant. We discussed this in our derivation, that thickness of oxide is a design parameter. It is already fixed. It's a constant. So why is this important to us right now? See, if thickness of oxide gets reduced to a point wherein the thickness is that of a few atomic layers, that means it will be very thin. Now when I'm talking about thickness of oxide, you should understand that I'm talking of the oxide layer that acts as the dielectric for our MOSFET, isn't it? This is what I'm talking about. Over here, this becomes my thickness of oxide. If it is getting so thin that it is only a matter of few atomic layers, what will happen? You remember last class when we were discussing about all the leakage currents, and we talked about the vertical uh, component of electric field and the lateral or the horizontal component of electric field, and because of that we had velocity, saturation and mobility degradation, isn't it? We had mobility degradation because of the vertical component. What did it mean? That because of the vertical component, what was happening, that the electrons that were supposed to move from source to drain would actually get attracted towards would actually move towards the gate, to the surface of the substrate, and because of that they used to get scattered, and that resulted into mobility degradation. So now all these things we have uh, brought it up, right? Now why am I bringing these things back is because if this oxide layer's thickness has become so thin that it is a matter of only a few atomic layers, then due to quantum mechanics, carriers, that is electrons and holes, okay, let's not say and, if it's an NMOS then NMOS, if it electrons, if it is not then it is a hole. All right, carriers will tunnel through the oxide layer towards the gate terminal. Okay, and what will happen if this happens? If my thickness of oxide is only a few atomic layers, my carriers will tunnel through the oxide layer towards the gate. And what happens next? Because of this, okay, when the carriers tunnel through the oxide layer towards the gate terminal, we call this, see, if electron is moving means what? Current is flowing. So we will call this as the gate leakage current. Okay, we call this the gate leakage current. Okay, and since we deal with either NMOS or PMOS, so the tunneling current, which is nothing but this gate leakage current only, in an NMOS is greater than that of the tunneling current of a PMOS if and only if, IFF means if and only if, silicon dioxide is the dielectric. That means the oxide layer is made up of silicon dioxide. At that point, if in both the transistors we have silicon dioxide as the dielectric, then tunneling current in NMOS is greater than the tunneling current in PMOS. Okay. So this is all about tunneling. Now the next topic is temperature dependence. Now, I don't know about you guys. If you are the current generation, if you have some elder siblings or elder cousins, you can ask them this. So, earlier devices, what used to happen is all these new phones or new smartphones that were launched, what used to happen, see, in India, when summer arrives, it comes with a blast. Okay, and when winter arrives, if you are in the northern part of India, then again it is coming with a blast. So in India itself, we have a very high temperature variance. Okay, this is point number one. Second point, why am I talking about your elder siblings or your elder cousins or relatives even? You can ask them, they might have encountered this, that during the summers, their smartphones, their devices, even if the devices were in their pockets or in their backpacks or in their purses, it used to get very heated up, even if they are not using it, even if they are not using it. And if you can ask them also, that if they used to get a call from their best friends, and we all know that a call with your best friend is naturally 2 hours to 3 hours long, even if you have just seen them in your college or university. So when that used to happen, again the device used to get a lot heated up. Another point is that, let's suppose I am talking or we are in a call with our best friend forever. Okay, so it is but obvious our phone will get discharged, isn't it? So what we do is we plug it in and then we keep talking. At that point also the device would get heated up. Okay, so this first point was only during the summers, and then these are all time, because we are always going to talk with our best friends, right? So nowadays these things are a rarity. These things are a rarity. Okay, these things rarely happen now. Why? Let us unfold that. Okay, now we have to understand that transistors characteristics are always temperature dependent. Okay, a transistor's characteristics are always temperature dependent. Why? This is because the the carrier mobility, that is either mu n or mu p, it depends on temperature. Okay, and what is that? That is mu t equals to mu t r multiplied by T upon Tr raised to the power of K mu minus K mu. What is this? Over here, T is our absolute temperature, Tr is our room temperature, K mu is a parameter or a constant, and the value ranges from 1.2 to 2. Okay, therefore by looking at this equation, we can conclude that mobility decreases with temperature. Now if mobility decreases with temperature, then the speed at which the electrons will travel will be degraded. If that is degraded, then it will impact on the current. Okay, so that every characteristic of a transistor is temperature dependent. Let us see how. We just started off with mobility, right? Let us see other parameters. So the our favorite threshold voltage also varies also varies with temperature. How is that variation, or what is that variation? Threshold voltage at absolute temperature is equals to threshold voltage at room temperature minus kVT T minus TR. This is the equation, and from here we can conclude that threshold voltage decreases with decreases linearly with temperature, and kVT is another constant parameter wherein the value ranges from 0.5 to 3.0. Another parameter of a transistor, that is sub-threshold leakage, also varies with temperature, wherein it exponentially it exponentially temperature dependent. So mobility, we saw that there is a, if we, mobility decreases with increase in temperature. Threshold voltage decreases linearly with temperature, and the sub-threshold leakage, okay, sub-threshold leakage is exponentially temperature dependent. Okay, it is exponentially temperature dependent. And the junction leakage increases with temperature. So leakage is not decreasing with increase in temperature, it is actually increasing with temperature. Okay, and amidst all this, if in totality, if you want to see, then the circuit performance actually decreases with increase in temperature. So all of a sudden, if the temperature of our earth increases during the summertime, if it is too hot to handle, at that time you would see that some of the older devices will lag, some of the older devices will get it'll hang, it will be very slow at performing its job. So this point, the whole circuit's performance wherein it decreases with increase in temperature, it is named as the negative temperature coefficient. Means with increase in temperature, the circuit performance decreases. Why? Because of all these points that we discussed. Okay, because of this cooling technology has been applied to the design. Okay, now you might have heard some ads previously, with cooling technology, I remember in Asus phones they had added the cooling technology in a smartphone. All right, you had your the earlier laptops, the laptop stands coming out with a fan. Why was that? So even if the processor gets heated up, the cooling fan will actually fan out the heat so that our device can perform better. Okay, so this is all about temperature dependence. Now the last point for today is geometry dependence. It is geometry dependent. Basically, when we are saying, so in one of our classes previously, I spoke about fabrication, wherein I explained to you in a very quick way that how the fabrication process happens, how the MOSFET is actually created. Okay, so that process is called fabrication. If you haven't attended that lecture, I will add the theory playlist within the description. You should go through it. It is very interesting. So when we are fabricating means we are building the whole MOSFET from scratch. We are building the whole MOSFET from scratch. Okay, and during that point I had told you that we have to create our n plus pockets. And how did we create these n plus pockets? We had to bombard at the given location. Okay, we will bombard with what? Dopants. N plus dopants, because our substrate is p type. And we will bombard means what? It is what you're thinking, like you might have seen in some documentaries that during World War I or World War II they used to drop missiles at those exact locations to kill the enemies, right? So basically we are dropping the n plus dopants at the locations where we need to create our source and drain. We need to create our source and drain. All right, now how did we get the location? So we got the location because previously, if you are a designer and I am your client, I am the vendor, I will tell you, hey, I need transistors with technology file of 4 nanometer. So from that statement, what will you understand? Oh, okay, technology file of 4 nanometer means all her transistors should have channel length of 4 nanometer only. So this much you know as a designer, that the channel length should be somewhere in the between. It cannot be at the side, it cannot be at the end of or at the bulk of p type, it cannot be on the side, it cannot be on either source or drain side. It has to be in the middle of my surface of our substrate. So from here you will measure 4 nanometer, and at the end you will understand, okay, somewhere here I need to create the n plus pockets, and there you will bombard the dopants. So in books, or when we are discussing or drawing the device structure for our theory purposes, we draw it like a rectangular small box. But if you are bombarding, see, at the end of the day, the p type substrate is nothing but a semiconductor, isn't it? And if I have bombarded it, it actually can't be a rectangle. What will it actually look like? It will actually look like this. And maybe the actual source and drain should have looked like this, but now it actually looks like the pink outline. Somewhere it is exceeding, somewhere it is exceeding the boundary, somewhere it is falling behind. See over here, here it is exceeding, here it is falling behind, here again it is exceeding, here again it is falling behind. Okay, so the n plus pockets can never be a proper, whatever, like a cutthroat or a proper rectangle. It will not look like that. Okay, so that is what I meant by this. So that means I had given you, as your client, I had given you the channel length to be 4 nanometer, but somewhere, see, where is it exceeding? It is exceeding in the place of my channel length. So at this point it is encroaching. So will I get a actual 4 nanometer here? No, it will be a bit less. And let's suppose on this part it is actually more than 4 nanometer, little bit extra on the drain side. It might happen because you are bombarding. Okay, so device dimensions may vary from what was designed. You are still designing for a 4 nanometer transistor, but it might vary. It might be very minutest dimensions we are talking about. Okay, so what is this geometry dependence? First example would be the same thing, the channel dimension that we spoke about. So W drawn and L drawn means the channel width and length dimensions, the specifications your client will send you. Okay, that was supposed to be designed may vary from the actual device due to fabrication parameter. Okay, this is my first example of geometry dependence. What is the second example? The second example is the one that we discussed right now. While creating the n plus pockets, in the device structure, that is source and drain regions, may diffuse under gate region. This implies that channel length gets reduced. Over here, see on the drain side, the pink outline, if you can see over here, that is encroaching where? Under the gate region. So what will happen? It will reduce the channel length. Okay, so these are the examples of geometry dependence. Therefore, see, these things are not under our control. Even if we are following up the best practice, the best use of all the processes, all with proper technology and everything, still these things will happen. It is not under our control. So we have to take account of these things. How will we take account of these things? By calculating the effective channel length and width. We cannot, stick with the older dimensions now. We have to take into account that there will be some encroachment of the n plus pockets diffusing under the gate region, okay, or that the specifications given to us will be different whatever we are designing, but in the actual device that we have already manufactured, whatever we have the device we have manufactured, okay, fabricated, means the device that you are holding right now, okay, it will vary. Okay, so we have to take into account all these things. Okay, so for that we have the effective channel length formula, where L effective is equals to L drawn plus X subscript L minus twice of LD. This is our effective length, and therefore we should also have effective width, because both are the dimensions of our channel. That is equals to W drawn plus X subscript W minus twice of WD, and this forms our effective channel width equation, wherein LD is the lateral diffusion of source and drain regions, and it decreases whom? It decreases channel length. WD is the diffusion of bulk, and it decreases the effective channel width, and XL and XW are nothing but factors by which the actual gate dimensions differ by. Okay, and it's a wrap for today's class. And with this, we have actually completed our non-idle IV effects. Remember, these non-idle IV effects are semester questions, and of course your internal questions, the 3 internals or the 2 internals you give before you actually appear your semester. It is mandatory that your teacher, your faculty, your professor will ask you about these. And if you are appearing for VLSI jobs, these are the questions where they will grill you, that how much do you know about a MOSFET's behavior in non-idle effects. Okay, and we are still on to road to 500 subs, and I'm really happy that we are growing, and the continuous support from all of you is actually filling my heart and making every day count for me. Thank you so much for all your support, and if you're watching this video, it's helping you out, and if you haven't yet subscribed, I would seriously request you to subscribe the channel and be a part of our tribe. Thank you so much. Stay happy, stay updated.